Okay, I think we'll go in and get started. I think a few folks will be joining us momentarily. Let me go ahead and open up in prayer, and then I'll give a sense of what we're going to be covering for today. So, dear Heavenly Father, Lord, pray that you would be working in the lives of each of the students in this course. Lord, I pray that you would help them to master the material that we're exploring, to get a better sense of what it means to be an engineer. And then for this class, thinking specifically what a system engineer would be like. Pray that you would help them to get their jobs in the profession that they seek to have in the future. I also pray that you would help in their spiritual formation, Lord, that you would help each individual to really to take in and to remember and to be able to utilize all the information they've learned from scripture, all of the theological concepts and method that they've got a chance to be exposed to, and give them interesting and creative way for faith integration. In Jesus' precious name we pray. Amen. Okay, well, this may end up being a little bit of a shorter lecture today, but what we're going to do is now get into this last section that we have in our textbook, and this is in the systems domain. And so we've gotten a chance to be thinking about a couple of things. Systems engineering, we've heard terms like top-down systems engineering. And then in the last lecture we spoke about was systems of systems. And so you're trying to integrate these things that are so large that each one in itself can be considered a system. Now we're going to be stepping up yet another level into something called enterprise system engineering. And I would say there is some relationship between these two, but this is maybe thinking in terms of like an operational capabilities that's centered on something. This can be more enduring rather than a certain limited time frame of what's going on with those system of systems that agreed to cooperation for so long. So I'll give an introduction with this slide, and the next slide I'll just read a couple sentences from our textbook, and it'll also help to give you some insight into what enterprise system engineering is. So it can be used to describe the people, the processes, the technology that interact with their environments to achieve the enterprise objectives. So that's one part. As the enterprise matures, components of the enterprise may become subject to addition, modification, or removal based on the external environment and other influences. So thus, it's not just like thinking like Hubble being a system. It's like thinking of space astronomy, and now there's Hubble and there's the James Webb Space Telescope, and there's other ones. That would be an example of an enterprise. It's not just one thing. So directly from our textbook for this chapter, it says enterprise systems engineering is a multidisciplinary approach combining system engineering and strategic management to address methods and approaches for aligning system architectures with enterprise business rules and the underlying IT architecture, development and implementation consistent with enterprise strategic objectives and the total enterprise systems and capabilities with diverse complex subsystems. So there's a lot of going on there, and I'll have an illustration of something that maybe you might be able to consider it in terms of an enterprise. And so then continuing on, the system engineering lifecycle can be used as this framework. And so this can be used for linking outcome-based engineering analysis and decision-making with enterprise strategic objectives, addressing methods and tools for managing complexity, determining measures of effectiveness, and assessing return on investments from an engineering perspective. So that's kind of a complex sentences, but that just gives you a little bit of an idea of what that might all mean. So what are the processes and components that are associated with this? So it has these, it has technology development. And so you can be seeing some of the things that we would see for an engineering life cycle, but now we're thinking it at the enterprise level. So technology, you have capability-based engineering analysis. We got a chance to be thinking about that early on when we were doing our development and exploration up here in the concept development phase for a system. And so we can see there's some overlap there in terms of methodology at the enterprise level. Then we have to be thinking about the enterprise. What does it mean for this whole aggregation of things that's comprising this enterprise? What is that architecture actually being laid out to be? What are the strategic technical planning things that need to be done? So strategic is not just like, what do I need to do today or tomorrow, but the larger, more important drivers that are associated with this. And finally, there's an enterprise assessment and analysis. And we've also got a chance to be thinking about the definition of enterprise system engineering, but then we can be thinking about what it would mean in detail for each one of these processes that we've laid out. So this is a picture that I found for ESA, the European Space Agency, their Space Operations Center. And so this isn't just dwelling on one spacecraft, it's dealing with all kinds of different assets. And you can think like a NASA Operations Center would be something like this. I was showing last time we had a picture for the International Space Station. Still, it is an aggregation, so you could consider that an enterprise, but this would be yet another. And so each time the launch a new capability, now it's flown into a larger space operations, then that's an entity that's integrated within it. And so here are just a couple of charts that now kind of try and highlight that difference between traditional systems engineering and enterprise system engineering. So for traditional, it's a well-defined boundaries of the system under development. For enterprise, the enterprise will continually incorporate and move other people, processes, technologies, and I would argue systems as well, responsive to the environment. Traditional, there's a reasonably stable operational environment, while in enterprise, the environment will be under continual changes based on user needs, improved technology, and different user demands. Traditional would have a set of agreed to requirements that are well-defined and stable, while in the enterprise requirements are broadly stated as vision statements and will evolve over time based on the user demands and external environments. There's also for a set of functions in the traditional side can be decomposed and have expectations of the overall behavior of the system. In contrast, the enterprise will have capabilities and behaviors of the enterprise will emerge dependent on the environment, participants, and external pressures. Finally, for a traditional, it would have a unified management structure, while enterprise would have the potential for conflicting objectives between people, organization, components, things like that. So all things are like that are possible. What might end up being some things that would come up from an enterprise in contrast to traditional. And then for an illustration of this would be an enterprise system engineering context. And so we can see that, well, these are the boundaries that we're stating are within that enterprise. I'm focusing on space systems as an example for what I've been using in our class. And so, but there could be multiple systems. It could be GPS. It could be different types of remote sensing systems. Maybe you're thinking about a mission to Mars or a precursor to that by looking at what can be done to the moon. And so a variety of systems are going to be there, various organizations. You can be thinking that there's a NASA, there's a European Space Agency, there's a Canadian Space Agency, maybe Japan with their space agency, all of that. So a variety of people, organization, systems, all of those are things that are coming into play when we're thinking about this enterprise. So you're trying to work out a set of objectives that would fit within this aggregation, but there's other things then that are outside of it, suppliers, partner that maybe you're leveraging, technology that you're trying to have insertion into that. The environment that it's dealing with. And so you can think of a space environment, maybe some things are low Earth orbit, maybe some things are high Earth orbit. And so all of those things. There could be competitions. And so maybe there's multiple things that are in this area. And plus, there could be threats of one form or another, maybe environmental or intruder threats, or so that gets into cybersecurity. All of those are things that could be within the realm of what would have to be explored. So those are just gives you a couple thoughts in terms of enterprise systems engineering and what a system engineer would be doing in the midst of that. And so this is other things that are captured related to this in this chapter. And so the first major thing I'll talk about is the process and components of system engineering, enterprise system engineering. And so there's the enterprise processes, there's the engineering principles, and then there's enterprise management. So for the processes, the 5 steps that are used that need to be thought about for the processes are the technology development, the capability-based engineering analysis, the enterprise architecture, strategic technical planning, and enterprise assessment analysis. And we got a chance to be thinking about that a little bit here when we were thinking about that. And so this is a little bit now thinking about it in a little bit more detail. And I refer you to the textbook to be thinking about this in yet greater detail, but I was just trying to highlight a few more things that are part of that. In terms of the principles that are associated with enterprise system engineering, you want to be thinking of the holistic approach. And so this whole thing is an entity of its own in terms of what we're thinking about. This is the enterprise that we're trying to consider. You want to be identifying stakeholders, and maybe you could have layers of stakeholders. Maybe there's entities that report to higher entities, and so you want to be identifying all of those stakeholders. What does it mean to have effectiveness in this enterprise? It means that these things, the different systems have to collaborate and work together in a coordinated way that meets the objectives that everybody is considering. These multiplicity of organizations have to be consulted and make sure that everything is working properly. There's a focus on enterprise interdependencies. And so you have position, navigation, and timing, say for GPS or the European Galileo system. Those are things that needs to be thought about. And maybe having some cooperative way of using all of those assets to help to give you a better sense of position, navigation, or timing, just to think from a GPS lane, if you will, that's part of this enterprise. You want to ensure stability and flow. You want to make sure that information is flowing properly, that everything is stable, so that you want to have this whole enterprise to be able to endure over a large extended time frame. And then you want to be encouraging leadership to support the behaviors that are necessary to make all of these components relate and connect and continue to work together as a team. And finally, to be open to experiments and gain further insights by looking at doing what if kind of scenarios. Maybe here's this new technology, here's this new system. How are we going to add it into our enterprise, or maybe we won't? And those decisions have to be thought about. And so experiments are a great way to explore that. And then you have to be thinking about management. There has to be an enterprise aligned strategic plan. And so management has to be in line with what the enterprise is trying to do. And so this comes back to the objectives, trying to juggle the priorities of the organizations versus the objectives of this enterprise and working that all together. So then the enterprise system engineering, there has to be applications to the different domains. And so maybe you're going down to some of those lower levels that needs to be explored, and also thinking of the challenges to the system engineering, the enterprise system engineering. What are some things we've talked about? Risk and risk matrices. And so what are the challenges that might need to be exposed and tracked? Those would be some examples of some things that are there. So it's a relatively short chapter, but we got a chance to get an introduction to enterprise system engineering. This is a little bit out of the sweet spot of what we're trying to cover in this course, but we at least want to have some exposure to that. We also talked about the processes and components that are associated with enterprise system engineering. So let me stop there and see if there's any comments or questions. You guys tracking that? You can just do a thumbs up if that's making sense to you. Okay, good. So these latter chapters aren't very long, and so this isn't going to take too much of our time. So I won't make this too long today, but I will have at least one more topic that I'm going to be referring to. And so this will be a little bit of a precursor that I think we'll have a couple lectures towards the end of the course where we can be starting to think about, well, okay, we've explored system engineering. We went through the whole life cycle for that from our textbook. And now we can be thinking about that in addition to the SysML modeling that we've done. And so what can we start to do? And so we have all these individual diagrams that you've done, and you've gotten a little bit of an idea of what that might do. But what we have in our textbook, one of our other textbooks here, and so this is Freudenthal that you all have, you're using the practical guide to SysML. And so just looking at the table of contents for that. And so we have an introduction to what system engineering is, what model-based system engineering is. Then we get some more specifics into the language, looking at one diagram type at a time. And then we have these other kind of chapters here that look at some of the cross-cutting relationships. And so now maybe we need to be allocating resources to multiple sub-entities within our design. And so that gets into the area of allocations. So then we have some other things about thinking about specific domains. And so we've been talking, at least the analogy I've been talking about is a NASA mission. Each one of you have chosen products in different areas. And so there can be some customization of SysML. I just got an article published where I was trying to use SysML to give insight into biological systems. If anybody's interested, I can share some of those details about that. Freudenthal also gives a couple examples of model-based system engineering and how you can be looking at that. And so there's a water distiller example and a residential security system. And so this is something that we've gotten a chance to be thinking about with some of the stuff I've been looking at the Freudenthal system engineering material that they have in the Magic System Architect, or I've been calling it Cameo Systems Modeler. Those are things that we have. So there are some things that are useful. And then another thing I would point out is there is a really extensive appendix. This is for all of the syntax for SysML. And so if you want to get a chance to get greater insight, I know we've been using visual paradigms, but that might be something that would be of use to have you be thinking about to give a broader perspective of what this is all trying to accomplish. So I'm just going to scan through this chapter a little bit here and try and give a little bit of perspective on some of the things that we can figure out from this. And so so this chapter describes how the allocated relationship is used to map from one model element to another to support behavioral, structural, and other forms of allocation. And so that is something that is useful, that these different diagrams aren't meant to just be in their own silo. It's meant to come together and help us to get a better understanding of the bigger picture. So beginning early in system development, the modeler may need to relate elements in the system model in abstract, preliminary, and sometimes tentative ways. So I would argue with the system modeling that you've done, that's where we've started. We've had things at a higher level. It is inappropriate to impose detailed constraints on the solution too early in the development of a system. Allocation is a mechanism for relating model elements in a way that provides guidance for the more rigorous relationships that are subsequent developed during model refinement. Additional user-defined constraints can augment the allocation relationship to add the necessary rigor as the design progresses. So you've had a start to what you've done, and then delving deeper into, say, one or more core areas. And as things go, there's going to be more constraints that are going to be identified, and that's going to ripple through the design. And so the overall design is going to mature. And so here's an example for an allocation of functions. You could also consider that activities. You can think of like the activity diagrams to components may be done early in the decision process. As design progresses, additional constraints are imposed to ensure that the activity inputs, outputs, and controls are explicitly allocated to component interfaces. With appropriate user-defined constraints, allocation can be used to help enforce specific system development methods to ensure the model's integrity. So I'm not going to read a lot more than that, but it just gives you some thoughts to be thinking about. And so this chapter is thinking about the allocation process, and there's some things that we haven't done in our diagrams, including this allocation, maybe getting to the next level, but you can start to see they start to relate one diagram to another. So here we have an activity diagram having some relationships that are being highlighted with a block definition diagram and an internal block diagram. And so this is an example of allocation activity, block diagram, and an internal block diagram. So remember, an internal block diagram is meant to be taking a block and expand more details on that. And so this is the focusing on the controller. And now we're starting to talk about allocations from other parts of our model. So I'm just going to do a quick survey about some things like this, just to give you an idea. So this is something that you can be doing in the process. You can allocate and have things like this. You can have I haven't tried this in Visual Paradigms as of yet, but you have a block definition diagram, and you can label something activity. I know there are some other labels that are available. You can have a block and then have more of a specialized block. That is something that you can actually do in Visual Paradigms. And then you can have these caveats that are associated. We've started to get more and more of these elements start to show up in our blocks when we start to relate one block to another. We start to look at some of the other diagrams that we've gotten a chance to be seeing as we do our model development. So those are some things that come up. We haven't talked about these tabular matrices, that allocation matrices, but this is something that can be done. I don't think this is something within the Visual Paradigm version that we're using we can easily do, but I will spend some time with our other tool that I've been showing you to give you an idea of what those things are all about and how that can be helpful. So you may want to spend some time going through this chapter, and I think it might be interesting as we now progress towards finishing up our models, and then what do we want to be putting in our final project report and presentation. It talks about the different kinds of allocation, requirements allocation, where now you go to the more specific type of details of what you're trying to capture in your design, what type of behaviors that you want to be capturing. So this is something that you can be doing, behaviors or functions. So both of these, so the term behavioral allocation generally refers to a technique for segregating behavior from structure. And the term functional allocation is a subset of behavior allocation, is referred specifically to the allocation of activities or actions, which are also known as functions, to blocks or parts respectively. And then you can have a flow allocation, where is often used to allocate flows between activity diagrams and internal block diagrams. So those just give you some idea of some of the things that you can be doing, that we start to relate these elements together. And the chapter continues to do some further development. And so here we're seeing an allocation of usage. So the functional allocation is shown here. But also structural allocation would be in a similar fashion. So this isn't giving us anything in terms of domain, but it's just giving us some perspective on how we can relate things that we have in an internal block diagram with an activity diagram. So I'll just scan through the rest of this to see if there's anything else that I wanted to highlight for today. So this is getting back to our surveillance system, which is one of the things that we have had a chance to be thinking about. And so maybe that might be a context for you to be considering a little bit more. And so you can be reading a little bit more about that in chapter 14. This is also has some more specifics about a surveillance system with having the ability to adjust the focus. And then we have the focus controller, which would be a particular block in a block definition diagram. And then highlighting behind here is this allocation matrix that we're also just trying to point out that that's part of what we have here, and things that we can putting together in an ever increasing, more detailed block model. So this is also just another parts of that, the behavior things that we're trying to capture with our surveillance system. And so some of the things in doing edge detection, that would be something. And so maybe you're in a challenging environment to trying to detect what is what. And so this is an image processing technique that can pull out some things that you're trying to take advantage of. And this is something that they have for one of their applications. They have a water distiller. So I won't go into this in detail, but this is something that's in a couple of chapters later in this textbook that gives a chance to be thinking about. So here's something for a power station structure. And so several of you are doing something that's related to power. So you might want to read up on this section to see if this gives you some greater insight into what you might want to be doing as you start to refine your model. So here we're dealing with flow. I mentioned that earlier. And so here we're relating an activity diagram to an internal block diagram. So the flow of information, the of how you're trying to be detecting your environment. So maybe that would be you detect an object and you're having that information passed on to another part of your system. So something's detected, and then based on what you get, then you're going to trying to get to an optimal focus for that. So then that infers that you need to have the ability to have a sharpness detector. And so this adjust focus, there's things that are allocated to a sharpness detector, which is down here. And so here we're showing a flow of information, a process that we're capturing in an activity diagram. So this is how we can start to be making a bigger story by showing how these things all come together. And now this is showing the activities and relating it to an allocation matrix. So we have this activity. Now we want to relate it to components or subsystems. And so this is where we can start to be seeing that there's going to be a relationship between the a measure pixel contrast with a sharpness detector, and an object flow is related to an item flow over here. And so those are some things that you can start to relate. This is another example of relating an activity diagram with an internal block diagram, as well as the allocation matrix. This is just some more with the adjusting of the focus. And this is an example of doing some structural allocations. So we have the focus controller, the motherboard, and so there's things in the focus control that is related to, we have a sharpness detector that's going to be allocated to the analog to digital converter chipset. And the focus optimizer is going to be allocated to the control processor. And then we have these other relatedness that we're laying out here. So what you're starting to see that the model itself can be useful. And one of the things I've been encouraging you all is to have like a paragraph description that sometimes, especially for a first viewer, they may need to get a better understanding of the context of what this is. And so I'm just trying to do that a little bit as I'm just scanning through this chapter, just to make a few points to have you start to be seeing some of that. So this is a little bit more complex example. So this is for the physical structure. So this was structural allocation of usage, and this was for physical connector allocations. And I'll just finish up here. This is once again our surveillance system. We're getting a chance to see it from another point of view, that it depicting the structural allocation of definition. This is the modeling the structural flow allocations. So this is now trying to show the relationship between the block definition diagram and the allocation matrix. And I think that's enough for what I wanted to capture there. So any comments or questions on what I tried to give a little bit of some insight from chapter 14 and Freudenthal? Or just give me a thumbs up if you're tracking from at a survey level of what I'm trying to let you guys see from that. Okay. Well, let me pause now to see if you all have any comments or questions or things that you might want to explore. And if not, what I would recommend, spend a little bit more time focusing on your models. And that's where I'm trying to give you some more hands-on type of work, which is typical of the kind of work that you do as a system engineer. So any comments or questions?
So are we making a separate allocations diagram or just using like the block body diagrams we've already made?
Yeah, I'll have to look and see if we can actually do an allocation diagram with visual paradigms, and I'll report back to you next week. I believe that that's something that we can't do, but I'll try and let you know, and we can explore that. Let me just try something real quick, and I don't know if I'm going to pull up visual paradigms first, and I'll share my screen in a second. See if I can. One of the things that does come with your edition is that you get the rights to get updates. And so I just got asked to refresh my install. Fortunately, it doesn't take too long. It's all written in Java. And so they just update those modules. So I'll share my screen again here. This is a different project that I've been starting to work on, so I'll close this one out. So, so if I wanted to do a new one, yeah, I don't know if it comes up. It's an allocation diagram. So I'm gonna have to do some more research and how you might do that. So, but for the Magic System Architect or Cameo Systems Modeler, when I start this application, it does say Magic Systems of Systems Architect. So, but I think there's been various products that they bought together and make them interoperable. Companies buying other companies and what have you. So I'm just going to show you this, and then we'll spend a future class to be talking about it. So this is another thing that's nice about it. I try to replicate this in visual paradigms, the way it organizes the diagrams. But when in visual paradigms, it also causes some issues. And so that's one of the things that is a concern. So here are some allocation matrices. So here are some examples of what those look like. So this is, so you have your structures over here, and then you have your physical architectures over here. And so I've collapsed some of these things. And if I was just to open up one of them, so since some of you guys are doing power related, if I open this up, you can see how some of this would look. So I collapse this again. So here it shows the number of 6, that there's 6 things relatedness between electric power and the power subsystem. So if I expand that out, here there's 4 in this, there's another one in that, another one in that. So you can drill down into lower and lower levels. So now we can see the relationship between the power manager and the battery, the power conditioner, the power distribution, the power subsystem, the power. This is another aspect that I'm not going to get into in too much detail, but there's other aspects of the power subsystem. I also can look the other way. So if I'm trying to see this aspect of the structures of the power subsystem, it shows that there's going to be 3 relationships with different parts of the structure. And so this can actually be something that's fairly useful. The chapter that we talked about on model-based system engineering from our main textbook introduced, there was an example of this that some of you may not have caught, but you may want to review that um, for that from a number of weeks ago. So that was from our chapter 10. So those were the parts. Well, I thought there was, oh, here it is. So this is what we got a chance to be seeing. So here you're relating the architecture. So this is the part decomposition. And so what is the relatedness between one part to other parts? And so having a relative balance of things rather than one module is like has 20 different relatedness and others have one. Maybe your decomposition of parts may not have been optimal, and so that might have been something that you might capture by being able to think about it from that point of view. So sorry, I don't have this in visual paradigms, but I'll do a little exploration and see what I can come up with. I think one of the things I did find was well, um, there, here was something that's not that, but you can get a list of requirements, but with the share version or the modeler, which is what I have, you at least can list them. And so there are some artifacts that kind of are giving you a little bit of a sense of some some things that you can do, but I'll just leave it at that. Okay, well, I think that's a good breaking point for now. Um, so I'm trying to go a little bit in depth for some aspects of system engineering, and in other areas, just trying to give you a survey and letting you think about the bigger picture. So I hope everybody has a wonderful Easter. We won't be meeting on Thursday because we'll have a few days off for Easter. So God bless you all, and I'll look forward to seeing you all next Tuesday. Have a good rest of your day.